pleasure to introduce our second Mnev speaker, Pavel. He will be talking about combinatorial models of topological quantum field theory.
Thanks very much. All right. So, well, I sort of decided what to talk about in the beginning and didn't quite decide what to talk about further along the way, but we'll see. So I want to start by talking about simplicial BF theory, which is kind of a story from an older paper. So it's a story about constructing a field theory on a manifold equipped with triangulation, where the fields are cochains of the triangulation, and you sort of construct it by starting from the continuum field theory and constructing a low energy effective action somehow, where this low energy fields are the cochains of the triangulation. And well, where to go from that? So there are kind of different options, and well, one option is to go to well, a combinatorial model for two-dimensional topological conformal field theory. So where somehow the precision function is a cochain, a non-homogeneous cochain on the complex subcomplex of triangulation of the surface. That's kind of, it's a work in progress, but there's something already done, and that's with Andrei Losov and Jackson Beck, who is here in the audience. So that's kind of one direction, and the other possibility is to go to kind of another story, which is called Fukuyama's infinity category. Which is a work with also Andrei Losov and Donald Newmans and Oliver Chekenets, and this somehow it's sort of it's a Morse flavored story, but it's also simultaneously another viewpoint in BF theory, and it's just another gauge fixing in BF theory and calculating a low energy effective action with using some other gauge. But the output has some kind of logical meaning. So anyway, so at the moment it's sort of well, it's a quantum course, so it's sort of by observing it, so we will project one of the two possible states. So I thought that I should sort of give one joke during the lecture and maybe one thought. So this is a joke and the other will be thought, or maybe the other way around. So it's up to you to decide where the joke is. So okay. Anyways, but you can tell me if one of the two stories appeals to you more. So. And then it will help me decide. Okay, simplicial BF theory. So motivation. So motivation, something maybe remote from the world of topological field theories, trying to discretize the algebra of differential forms on an interval. So discrete algebra of the interval, algebra of differential form in the interval. So I want to look at the interval from 0 to 1, and well, it has the algebra, the algebra of differential forms. So it's a commutative differential graded algebra. It has a differential going from 0 forms to 1 forms, and it has a wedge product. So then the desire would be to construct some sort of a finite dimensional model for this object. So this is kind of some infinite dimensional graded vector space with some operations. So the desire would be to create some finite dimensional model for it. And here, in well, the operations would be supported on some finite dimensional replacement of differential forms. And one idea here is to take some cochains or simplicial cochains of the standard triangulation of the interval. So it's 2 zero cells and one cell. So let me call those cells 0, 1, and 0, 1 is the bulk cell. So we want to try to model the RAM algebra CDGA here on cochains. Well, let me call this model omega discrete. So discrete somehow forms of the interval. So, well, then as a graded space, it will be a graded vector space. It will be a span of three basis elements corresponding to the two ends of the interval and the bulk of the interval. Let me call the generators E0, E1, and E0, 1, and their respective degrees would be 0, 0, and 1, corresponding to the, well, standard grading corresponding to the dimension of cells. So 0 cell, 0 cell, and 1 cell. So, okay, this is span of the ground field. Let's take it to be reals. So it's the, so elements here are, well, linear combinations of these basis vectors. So x0, x1, and x0, 1 are reals. Now, how about the operations? So, okay, so we need to invent some sort of a discrete replacement for the run and for the wedge product. So for the run, there's kind of it's natural to replace it with the cellular coboundary operator, which maps E1 to E01 and E0 to negative E01. So that's the cellular coboundary operator, and sends E01 to 0. So how about the wedge product? So, okay, so one kind of natural guess for the wedge product is to do the following. Okay, so let's try to invent some sort of a multiplication table. So first of all, if I take the product of 0 cells, then well, I would like the situation to be compatible with kind of base maps, inclusions of points into that interval. So it's natural for me to ask that E0 where E0 is E0, E1 where G1 is E1, and E0 where G1 is 0, and E1 where G0 is 0. Now, if I take the product of E0 with E01, so okay, so let me suggest, so actually there are choices here, but let me suggest the choice which is symmetric with respect to the reflection of the interval. So this is the symmetric choice. There's also a standard non-symmetric choice, which is called Alexander-Whitney cup product, but let me do the symmetric one. Okay, and E01 wedge E01 is 0 just by degree reasons. So that's a multiplication table. Kind of we just guessed it from some natural considerations. So so the compatibility with space maps, supercommutativity, symmetry of the interval. That's why I put this 1/2 here. Symmetry of the interval. And also, we would like E0 plus E1 to be the unit for the product. Unit for the product. Okay, so kind of reasonable requests, and okay, so that resulted in this multiplication table. Now we might ask, okay, so the algebra has certain relations between the operations and properties. Are they satisfied here? So the relations in the de Rham algebra are that d squares to 0, which is kind of also is true in this discrete context just by degree reason. So I take a 0 cochain, d maps it to 1 cochain, I take d again is 2 cochain, and there are no 2 cochains in this business. So of course d squares to 0. Now the other relation is the Leibniz identity. So d of the wedge product will be equal to d alpha wedge beta, and then plus some sign, let me default to sine alpha wedge d beta. Well, it turns out that this is also true here, so no problem. Also works for this discrete model. Now, how about the associativity? So that's another property, the associativity of the wedge product. So, well, is it true that these two expressions are equal? Well, the answer is that no, it's not true. They are not equal. So associativity fails. So, for example, if I take E0, wedge E0, wedge E01, then, well, okay, this is just E0, so this is 1/2 E01, and on the other side, I would have, let me put the parenthesis in the other way. So that's 1/2 E01, then I wedge again with the 0, I get 1/4 E01. So that's not equal. So associativity fails, but it turns out that one can restore it in some sense, in some relaxed, so one has some relaxed version of associativity. So associativity can be restored in the so-called up to homotopy sense. Can be restored in an up to homotopy sense. What does it mean? Well, it means that I should look at the associator, so the difference of these two expressions, and that this associator is the exact in the appropriate sense. So it means that if I take three, let me call them alpha 1, alpha 2, alpha 3, if I take three chains, and then look at the associator, then, well, it turns out that I can invent certain operation, M3, so I can invent certain operation M3, which eats three inputs in chains, or I call them discrete differential forms, and spits out single discrete form. So I can invent such an operation such that the associator is equal to d of M3 applied to alpha 1, alpha 2, alpha 3. So 3 is one of the, it has three inputs. It's a trinary operation. So, okay, so there are some signs which I think like that. And 3 of d of alpha 1, alpha 2, alpha 3. And then some signs depending on the degrees of alpha 1, alpha 2, alpha 3. So let me not write them down. And 3 of alpha 1, d alpha 2, alpha 3. And 3 of alpha 1, alpha 2, d alpha 3. So the right-hand side is sort of M3, where either the output or one of the three inputs is hit by the Combinatorial neighborhood. So it turns out that you can invent such an operation M3. I will write it as a part of a bigger structure in a moment, what essentially is. Well, and in fact, this is a part of some larger structure that you can come up with. So in fact, one can extend this sort of operations D and wedge product on the space of cochains. So let me call it D. Let me introduce another name for it, M1, and wedge product I can call it M2. So I can continue to a sequence of operations, and the sequence of operations has the name an A-infinity algebra, to an A-infinity algebra structure, which is a sequence of operations M1, M2, M3, M4, and so forth. It's a sequence of multilinear operations on this space of discrete forms. So the MK is a k-linear operation. And well, these operations are supposed to satisfy a sequence of relations, and they are just a continuation of this sequence. This relation, and then this associativity up to homotopy, and then there are some subsequent relations. So let me write down the general relation. Well, I'm writing everything up to science, but well, one can write science also in principle. So okay, so the relations are like that. So you fix n, and then you're summing over P, Q, and R such that their sum is equal to n. P and R are negative, Q is greater or equal than 1. So then you take M P plus R plus 1 of a bunch of inputs, of P inputs. Then in place of the next input, you put M Q of the next bunch of inputs, of P plus 1 dot alpha P plus Q, and then the remaining inputs alpha P plus 1 the dot alpha P plus Q plus R, which is the same as N. So the sum should be equal to 0. So what does this mean? In other words, I have my kind of sequence of elements of my space, alpha 1 through alpha n, and then I select a subsequence and hit it with one of the operations MQ with some additive Q, and sort of replace this substring with the output of this MQ, and then hit the result with M of appropriate arity, and I sum over the ways to select a substring. So it's a double sum. Looks like a triple sum, but the conditions of impact, it's a double sum, essentially over the start and end of this string. So okay, so these relations are called higher associativity relations or homotopy associativity relations, or for short, infinity relations. So one thinks of them as quadratic relations on structure constants of these operations. So another kind of graphic way, standard graphic way of drawing these relations graphically. So I have well, a bunch n inputs. So and then I okay, I have inputs I don't know, alpha 1 okay, let me just go like that. So inputs 1 through P go as first inputs in some operation. Then I have the next next Q tuple of operations go to an in operation. Then its output goes as an input as the next input of this M P plus R P plus Q P plus R plus 1. This is M2, and then the remaining inputs go here, so P plus Q plus 1 and up to M. So so you have a bunch of inputs where you put in your element space, and then you hit a kind of a sub collection of these inputs with M and put it as an input together with the remaining input forms into another type. So such a sum with appropriate signs is equal to 0. So sum over this substrings. Okay, so this is the infinite relation graphically. So okay, what I gave here is a definition of an infinite algebra, but what I'm saying is that in this example one can construct an infinite algebra. So here's a definition of infinite algebra: just a sequence of operations on a graded vector space satisfying these relations. So by the way, so for instance, for n equals 1, this relation, if you unwind what's written here, is just the relation that m1 squared to 0, or differential squared to 0. For n equals 2, this relation is the Leibniz identity between m1 and m2. For n equals 3, it is this relation, the associativity of the homotopy. But what I'm saying is that there's an explicit infinity algebra. So let me tell you what it is. So m1 and m2 I already explained over there, but let me explain the higher m's. So the higher m's in our example, so on the discrete. So I have that m. It's convenient for me to talk about the operation of arity n plus 1, just to harmonize the formulas for n at least 2. So that means I'm describing m3 and upwards. So it's an operation that's so I can tell you what happens if I feed to it several copies of E01, and then at the next input E1, and then several copies of E01. So then the output of this operation will be, well, it's some number times E01. And this number here is kind of curious, so you need to write correct numbers here, otherwise the relations will not work. And the correct number is some sign times the binomial coefficient times the Bernoulli number. So Bn here is a Bernoulli number. So somehow in the structure, Bernoulli numbers make appearance. So and if I do the same but replace E1 with the 0, it's minus the same answer. And anything else, any other sort of inputs, the output will be 0. So the claim is that these operations do satisfy these relations. It's a non-trivial statement. It's some kind of non-trivial quadratic relation between Bernoulli numbers. So, well, a reminder of Bernoulli numbers. So here, let me just write several few Bernoulli numbers. So 0 Bernoulli number is 1. The third one is negative 1/2. Then it's 1/6. And then it's 0, and then it's negative 1/30. So Bernoulli numbers tend to pop up in very surprising places in math. Maybe you heard that Bernoulli numbers appear as orbifolder characteristic of the moduli space of curves. Well, here's another strange place where they appear.
I'm a little curious about the grading. So like, if I think of it, like if I have too many copies of E01, won't I automatically be 0?
Good question. So, okay, so the degree of the, in an A-infinity algebra, the degree of the operation mk is 2 minus k. Right, so in particular for M1 is differential, it has degree +1. So M2 is a product, it has degree 0, M3 has degree -1, and so forth. And it should, because M3 is a homotopy for the association, so homotopy should tell us 1 degree lower. And so the higher M's are their kind of higher homotopies. And with this convention, the degree works. Okay, yes, please.
Question. So like if I would think about discrete analogy of like manifolds, I would think of simplicial sets.
So simplicial complexes, yeah, or semi-simplicial sets, if you like. Yeah, I will not have degenerations, but they'll have base maps.
So isn't there like a cup product on like?
There are different cup products, yes. So there are different cup products. There's, for instance, there's the standard Alexander-Whitney cup product, which is not commutative. It's only commutative up to homotopy. But that's a choice that you make when you're talking about cup products of 4 chains. And here I'm making a choice to make it commutative, but then it's not associative. And then you want to write. That's why I'm going with this. Yeah, I'm going to indeed A-infinity structure on 4 chains. But I should say that this commutativity actually corresponds to the fact that this is what is called C-infinity structure, which is commutative A-infinity. So Owen.
I have a question, which is also heading towards giving an explicit quasi-isomorphism between these two.
I was not right now. So let's see. So
Big.
isomorphism, yes. So yes. Right. So how does it go? So yeah. Well, essentially, in some sense, yes. So the quasi-isomorphism. How does it go? So it's yeah. It sends like a 1 form on the interval to the integral of the form of the over the interval times E01, and then it evaluates the 0 form at one end and multiplies by E0, and evaluates on the other end multiplies by 1. Yeah.
Sorry, Pavel, when you answered Connor's question, you said, oh, the degree of this Mn is blah, blah, blah. Would you mind writing down the degree?
Yeah, so degree of, so in these notations for mk is 2 minus k. For this was mn minus 1, so it's 2 minus n minus 1, so it's 1 minus n. So that's the degree of this operation. Yeah. So yeah, for A-infinity algebras, there are different ways to describe them, and sometimes it's described as a structure of a sort of space with a shift by 1, which comes from the bar construction, and then all operations have degree +1. But I prefer this way because then usual algebras are an example. Okay, maybe yeah. Since we're talking about Bernoulli numbers, just a reminder that they are generated by, well, you could say hyperbolic cotangent, but the generating function for them is, well, okay, the standard way to write the generating function is like that. It's a generating function for, oops, for the good interface. Okay, now this was some sort of a claim that, well, there is this kind of equations that you might want to solve, somehow higher associativity equations, and this is a solution. And you could consider this as a guess, but in fact, these operations can be constructed, not just guessed. As a solution to this equation can be constructed rather than guessed. So this is kind of my next point. So operations Mn can be constructed rather than guessed. Rather than guessed. And this construction is somehow from field theory. So they are constructed as sums over trees. So, well, roughly speaking, the operation Mn will be a sum over binary rooted trees with n leaves. So that's where this is going, and then these graphs appearing here, they can be interpreted as Feynman graphs in some perturbative computation in the field theory. Feynman graphs for a certain computation in field theory, more precisely for certain, well, what's called fiber BD integral, or a more physical name for this is a computation of an effective action on some slow fields. So, and then in terms of this computation, the relations have a particular meaning. So, okay, so somehow the dictionary is that the operations that we were constructing, they correspond to some operations and correspond to some kind of low energy effective action for some field theory. Well, I kind of already told you the name of this theory is called BF. That's the name of the theory, and we'll talk about this in a second. And then equations, A-infinity equations, they correspond to, well, some equation for this effective action, which is called Badalin-Wilkelinsky master equation. One can say that it's, well, okay, somehow in symbols, this is that Poisson bracket of S effective with itself is 0. Or the, okay, that's the classical mass equation, that's also the quantum mass equation that we'll discuss. And in some sense, this is the statement that the effective action is compatible with pH symmetry. Okay, so somehow, yeah, so this algebraic structure can be recovered from computation in field theory. And now, at the end of the motivation, I want now to go to the field theory part. So, okay, please stop me if any questions. So, all right. Let me see. There is something maybe. So now I want to talk about BF theory. Wow. So
at the beginning, you said there's another way to construct a wedge product, right?
yes.
Does it also come from the field theory?
I don't know. So that's a good question. So maybe one can sort of play. I mean, the object one can play with it is choice of gauge fixing. So maybe somehow you can change the gauge fixing to obtain the I don't know, the Whitney structure. Maybe.
Gauge fixing rather unique.
How we get?
Is the gauge fixing in 1D rather unique?
I have to start with this. Have to start with this. So once you have chosen inclusion and projection, then it's fixed. But maybe you can play with those. So, but I guess the honest answer to the question is that I don't know. So, all right. So BF theory. So BF theory is a relative of Chern-Simons theory that Konstantin was talking about. So it appears it was sort of invented later. It appears, for instance, in 2 dimensions, it appeared as 2-dimensional Young-Mills at 0 coupling constant. In 3 dimensions, it's also it appeared as some sort of a double version of Chern-Simons theory. But BF theory exists in general dimension. Yeah, and in a way, it's an easier theory than Chern-Simons, easier to deal with. So let's fix M, a closed d-dimensional manifold, and let's fix a Lie algebra, a finite dimensional Lie algebra of coefficients. So then the classical action of BF theory is the integral over M of, well, I will tell you what the fields are, but they're denoted A and B. So so this is the action, and here the fields are A is a 1 form on the manifold with coefficients in the algebra, and B is a d-2 form on the manifolds with coefficients in the dual of the Lie algebra.
So do you use 3, you would change it to a D-man, okay. Sorry.
Yes. Yes. Right. So for instance, this expression, well, it's so I should be thinking of A as a connection 1 form for connecting a trivial G bundle for G, the group integrating the algebra G. So then the expression here is the curvature to form of that connection. So I can just rewrite it as I take the curvature to form, which is a Lie algebra valued differential form, and then I wedge it, I pair it using the wedge product now with my d-2 form. So I'm doing the wedge of the differential forms, and I'm pairing the algebra with its dual. So the result is a number valued d form, which I can subsequently integrate. So the name BF theory just comes from this notation. So BF doesn't stand for any 2 people. Also, it doesn't stand for background field, which I think was for ages written on Wikipedia. If you look up BF theory, it doesn't stand for background field. It just stands for these 2 letters. So okay. Now I should say that well, certainly there is a generalization of this picture where, like a more geometric version, where I consider some principal bundle over the manifold, some principal bundle with group G, such a group G, which integrates the Lie algebra. So then I can say that A should be a connection on the bundle, and B should be a d-2 form with coefficients in the coadjoint bundle. Then this expression again makes perfect geometric sense. But let me actually not go to this generalization, but work with the trivial principal bundle. This generalization doesn't change that much, so everything can be generalized quite straightforwardly. So okay, now looking at it as a classical field theory, so it has equations of motion, for instance. So the critical point condition for this action, and the equations of motion are that the curvature of the connection vanishes, and that B is a horizontal form with respect to that connection, or a covariantly constant form. So B sub A is a covariant derivative determined by the connection. So furthermore, this action has a symmetry, so gauge symmetry, actually 2 gauge symmetries, 2 different gauge symmetries. So one is kind of the usual one, rotations in a fiber-wise rotations in a principal bundle, which act on the fields in a kind of standard way. So here there's a formula that Konstantin wrote on the board. So let me write it also. So that's how, for simplicity thinking that our group is a matrix group, then that would be the formula for the gauge transformation, where G is a map from the manifold to the group, and B just conjugates again, I'm thinking of the group as metric group to write down these formulas, but one can write them for a general group also. Then you have a coherent action called the group element here. So the generator here is a map from M to the group. That's kind of symmetry 1. But then there's a symmetry 2 here. And the symmetry 2 is not changing A, but then it shifts B to by an exact term. So where tau is a d minus 3 form of M with coefficients in G star. So yeah, so there's this second gauge symmetry here, and well, you can notice that if you shift B by such a term, then by Stokes theorem and Bianchi identity, that doesn't change the action because dA of the curvature vanishes. Okay. Then, in fact, there is somehow higher gauge symmetry here in the game, namely that if your pair AD solves the equation of motion, so you have a flat connection and a covalently constant field B, then if I shift tau by dA of something, then those two values of tau correspond to the same gauge transformation. So there's reducibility of this group acting on fields. So this is the case of higher gauge symmetry. So the way to deal with this gauge symmetry is Battalion-Wilkowski formalism, and I'm sure that Konstantin will be talking about some generalities of the formalism, but let me just say how it works out here. So that means that I will need to extend my space of fields by adjoining new fields to the game. So there will be new odd fields, ghosts corresponding to generators of gauge symmetry. And then sort of then higher ghosts corresponding to the structure, reducibility of gauge symmetry, and kind of adjoint or anti-field for each field. So there will be our usual fields A and B. So for some reason I'm drawing them in some weird way now. So A is a one form, and it has internal grading 0. I should some color here. A has internal grading 0. This grading is called the ghost number. Now there will be an infinitesimal generator of such a rotation, such a fibroid rotation, so a Lie algebra valued 0 form. That's another field that will be in the game. It will have degree +1, and that's the green number is the ghost number. Now there will be, okay, B is a D minus 2 form, and it has ghost number 0. It's a classical field, so objects in ghost number 0 are classical fields. And then there will be the ghost, let me also call it tau, but now it will be an odd object corresponding to this H symmetry. Let me call it tau 1, actually. So it will be a D minus 3 form, which is odd, of ghost number +1. And then there will be an object corresponding to such shifts. That will be a higher ghost, or degree 2 ghosts, so ghost number +2, which will be a D minus 4 form. And there will be a tower of higher ghosts here up to D minus 2, which has the degree 0 and ghost number D minus 2. So, and then there will be sort of reflections of each field, kind of a conjugate with respect to the symplectic structure that I write for each of those fields. So there will be D dagger, which would be a 2 form of degree, of internal degree -1, and then tau 1 cos, and so on, tau D minus 2 cos of increasing the round degrees up to D, and of those numbers -2 and so on, 1 minus D. And okay, so those are kind of reflections of these objects, and there will be also A cos C cross, and that's the end. Okay, so this is D minus 1 form and D form of those numbers minus 1 and minus 2. Okay, so this is a whole lot of fields, and turns out that I should consider their sum. So what I have here is two kind of new fields, two BV superfields, and they are non-homogeneous differential forms. So let me call them A curly and B curly. And they are non-homogeneous differential forms on M with coefficients in the Lie algebra and with coefficients in the dual of the Lie algebra, respectively. The two non-homogeneous differential forms. Then the BV symplectic structure of BV2 form, or the old symplectic structure on the space of fields. So the space of fields will be just the sum of these two spaces. Space of BV fields will be just the sum of two copies of differential forms. So the symplectic structure will be given by what we call it omega. It will be the integral over M delta B, which this should be B curly, this superfield paired with delta A. So in other words, if I decompose it into components, it's a sum over species of fields. So which is in the sequence of letters A, B, C, tau 1, and so on, tau B minus 2. So for each species of field, I would have the integral of delta P paired with delta P cross. So somehow this cross notation just exactly means so that oh sorry, this is plus, this is not cross. So that B is matched with B cross, A cross is matched with A, and so on. So this is the odd symplectic form of degree -1. So the total, sorry, the internal degree or Gauss number of each term here is equal to -1. If you look at it.
I'm sorry, this delta, that's the Durham.
Yeah, delta is the RAM on the space of BV fields. I have the kind of space of BV fields now, which is two copies of differential forms with some kind of internal gradings. Well, I guess with correct grading that we write N1 here and how's it D minus 2 here. So yeah, so this is a graded vector space equipped with this degree -1 symplectic structure, and delta is a de Rham operator here. So yeah, I'm distinguishing delta with D. So D straight for me means kind of a geometric de Rham operator on forms on M. Whereas delta means de Rham operator on forms on the space of fields. Okay, now the PV action here. So PV action. So okay, so generally constructing a PV action for a classical gauge theory is it's a non-trivial business. So it's a solution to some kind of homological perturbation problem. So you need to start with the classical action and then add to it terms generating the gauge symmetry and add terms corresponding to the algebra of the algebra of gauge symmetry, and then you're trying to add more and more terms so that the resulting action satisfies the classical master equation. Let me just call it S. That the Poisson bracket of S with itself equals 0. So generally constructing the BV action for a classical field theory is a complicated business. Poisson bracket corresponding to omega. But it turns out that for a class of gauge theories, which includes the BF theory, one can construct these objects, the superfields. So put together classical fields with generators for gauge symmetry and for higher gauge symmetry and their sort of reflections, the anti-fields. You can put them together into superfields and writes down the action, which is just the formula for the classical action, where you formally substitute the superfields. So that's kind of some very strange manipulation. So you took the original classical action, which was written here, and then made the letters curly. And the curly letters, they are these non-homogeneous differential forms. So it's not true that you can deal with any gauge theory in such a way, that starts with the action in such a way. It happens with a class of gauge theories, which are called AKZ models. So AKZ stands for Alexander Kontsevich Schwarz Zaborowski. They're kind of topological sigma models with gauge symmetry.
So there's no difference between the D and the delta here, right?
No, they are different. So D is the Ram operator on M. So it takes a differential form on M and hooks up to the differential form 1 degree higher. Delta was the Ram differential on the forms on the space of fields. Right. So this only, what does it leave? It's a two form on the space of fields. So the space of field is the infinite dimensional Fresnel manifold, graded Fresnel manifold.
Glad I asked, since I didn't understand the answer that you first gave. Okay.
Sorry, yes.
Right.
Yeah. Yes, so yeah, in terms of variational bicomplex that corresponds to the horizontal and vertical differential. So one is D, the other is delta. Okay.
It's also not true in all AKC models, but it's the assumption.
I thought that at least for a linear target, that should be true. I hope so.
Only on the positive degrees target.
I don't think so. Well, maybe I should think about this. So anyway, so this is an example of a AKZ or AKZ model, which it's sort of a separate story. So in a KZ model, you are thinking of the space of fields as the mapping space between two DG manifolds, differential graded manifolds, where the source is the shifted tangent bundle of M, which has its own homological vector field corresponding to the Deron operator on M, and the target is G shifted by 1 plus G star shifted by -2. So somehow this is a pair of DG manifolds, and the homological vector field on the target corresponds to the Chevalier-Eilenberg differential of the on cochain of G with coefficients in the module given by the symmetric powers of G star. So anyways, it's a mapping space between two DG manifolds, so you can actually have a cohomological vector field, so vector field of square 0 on this mapping space, which corresponds to a kind of acting on this mapping by vector field here on one side and by homological vector field on the target on the other side. So and then one can also construct a natural symplectic form on the space and the Hamiltonian for that vector field. So and anyways, so maybe I should not go to the depths of the construction, but I wanted to say that BF theory is an example of that, and Chern-Simons theory is an example of that, and Poisson sigma model is an example of that. So that's a bunch of very nice examples of AKZ construction. So these are the cases when it's somehow easy to write down the solution of the mass equation. So okay, now, well, I want to say that the action here satisfies the classical mass equation. And with a certain regularization, it satisfies also the so-called quantum mass equation, which is different from the one above by an extra term, which this extra term is tricky and requires care to define. But sort of naively speaking, this operator called the DV operator is the integral over M of the second variational derivative in the A field and then in the V field at the same point. And this is sort of a singular expression when you hit a local function by this object, so it has to be regularized.
How can it satisfy both of these equations? So that is the delta is 0?
So you can,
So how is it that it satisfies both of these equations?
yes, yeah, exactly. It means that separately those are both zero. Yeah, they're both, yeah, exactly. Okay. Now, okay, so now I want to actually switch to the kind of finite dimensional model for what's going on here. So, okay, the idea is that we want to think of BF theory, as associated to, in some sense, associated to, and I should put it in parentheses, to the Durand algebra, of forms on the manifold. Then we want to construct somehow the low energy effective action, the low energy effective action on cochains of the triangulation, on cochains of that triangulation. And then, well, this will be some kind of a field theory object, this low energy effective action, but this will be some kind of power series in fields. And looking at the monomials there, just looking at those monomials, I will read off the algebra structure on the cochains. Read off from the result the algebra structure on the cochains. So that's the plan. But now, okay, so what's kind of annoying in what I was telling you? The annoying thing is kind of infinite dimensional objects. So the Durand algebra, it's too large. So let's kind of go to a simpler situation and talk about kind of finite dimensional model for this. So let's hook up some kind of finite dimensional model for BF theory. So let me call it abstract BF theory. Kind of forgetting about locality. So let's fix a graded vector space, which is complex with also a bracket. So I want it to be a differential graded Lie algebra. I want an extra little condition here. I want it to be unimodular. That means that if I take, that means that the super traces of matrices of a current representation are 0. So for any x in the algebra. So that's unimodularity property. That's okay, that will be necessary. So okay, so let us fix some basis in here. And well, the things that I will be saying, they are independent on the choice of basis, and just convenient to think about some basis in here. And E with upper indices, that will be the dual basis in this star. So I'm thinking of V as being finite dimensional. So then I want to construct a kind of a BD theory or BD package. Construct the BD package or BD theory, which I will call the abstract BF theory. So BD is Batarin-Wilkowski. BF is not any people in particular. Again. So, okay. Now, fields in my in this business are V with a shift by 1 plus V star with a shift by -2. So, and here I will call A and B. So So then I have the field A and field B. So with A is the sum of basis elements in V times some kind of coefficient. So these coefficients are coordinates on the space on the space of fields. So they're coordinates on the first term in the space of fields. And B is BA, EA, and BA are coordinates on the second term. So these are my two superfields. Well, I should be writing them as curly ones compared to that, but let me not write curly letters here. So the symplectic form is just corresponding to the canonical pairing between V and V star. And the action, and this will be the DE action. So it is, well, essentially the same formula as what we had in the beginning. So this is a polynomial. It's a cubic polynomial on the vector space F, the space of fields, with coefficients given by the structure constants of the algebra. Structure constants of the algebra. And what do I mean here? I mean that if I write this using this expansion in terms of basis, I will write it as well, components of the B field times the matrix of the differential in my basis times the components of the A field plus 1/2, and then the components of the structure constants of the bracket times B A B A C. So that's quadratic term and the cubic term. This action satisfies automatically the quantum mass equation.
Sorry, there's like 3 A's on the left-hand side. Should I expect like a conservation of indices or?
Yeah, sorry, on
The left-hand summand has like 2 A's in the upper position and 1 A.
Oh, thank you. Okay, yes. Now, this action satisfies the mass equation. So it satisfies the classical mass equation, which is that Poisson bracket of S with itself, the Poisson bracket of S with itself is 0. And actually, if you write it out explicitly for this cubic polynomial, there will be term which is all terms will be linear in B, but there will be a term linear in A, quadratic in A, and cubic in A. So they separately have to vanish for this to be true. So, and their separate vanishing corresponds to the properties that d squared is equal to 0, that one has Leibniz identity between d and the bracket, and that one has Jacobi identity for the bracket that arises as a coefficient of, if you look at the cubic term A in the Poisson bracket of S with itself. Now, the quantum mass equation, that's, well, okay, that's again, that's half of S minus H bar delta S. Vanishes, and again, since classical mass equation is true, it means quantum mass equation means that additionally the Laplacian of S vanishes, the d Laplacian vanishes. So that's tantamount to those three identities plus unimodularity. Unimodularity that I asked for, which is written here, or in terms of structure constants, that this contraction of the structure constant of the structure tensor vanishes. So, and then, okay, so I have 12 seconds. So from this point on, we'll construct we'll induce the effective low energy theory on a subcomplex, and then on a subcomplex of V, or rather on a deformation retract of V. And then we'll look at what it looks like. It will be written as a finite dimensional integral, which you can expand in Feynman diagrams. So we'll understand that answer and read off the A infinity algebra. Actually, quantum L infinity algebra on the subcomplex. That's what we will construct. And then we can apply the same for the de Rham complex going to triangulations. And that would be sort of going back to the topological field theory and low energy model there. Thank you very much.
Questions for Pavel?
Can you say something on the omega and that final bracket between those
Sorry, something about what?
Actually, I guess like, can you do something like expanded the coefficients for S? Can you do something similar for OMX?
Ah, yes, of course. Sorry, where is my, yes, of course, of course. That's just sum of delta B A which delta A, sorry, where's me? Yeah, like that. So it's like the standard symplectic form dx dp dq, right? But instead of p and q, I have sort of this pair of coordinates on the space of fields. It's a constant symplectic form on the vector space.
Not a very intelligent question. I just missed what you said on the last whiteboard at the bottom.
I said that
I can't read the top line either. So maybe just move it down a little bit.
sorry, yes. I was saying that that the kind of field theoretic object that are associated to this algebraic data satisfies the quantum mass equation. And the fact that it satisfies quantum mass equation corresponds to certain algebraic identities on the left side. And I listed those identities. That just from looking at the various terms in the, well, either bracket reflects with this or it terms in this expression, which also has a part. All right.
Other questions?
Yeah, just to clarify, so you're saying unimodularity, which is an abstract concept in terms of the structure constant is expressed by saying FA AB is 0.
Absolutely. And yes, and that means sum over A, right? So I always imply the summation convention. Yes.
This naive question is if I just said it's a DG Lee algebra, if I said L infinity algebra, could I put in like the full like Maurer-Cartan?
Absolutely. Great question. Yes, you could do that. But or rather, for L infinity algebra, you would have that, but you would not have this. To have this extra thing, actually we'll discuss. Actually, we'll come there. So you need an L infinity algebra supplemented with some kind of quantum or one loop operations, which needs to satisfy some extra relations, and then you will have that also.
Thanks.
Okay.
Okay, let's thank Pavel again. Right now, we will break for lunch. We have a 2-hour break. I think in your welcome packets, there are a list of several dining options around campus. They're open over the summer now. We will resume at 2 o'clock back in this room.